Ask my instructor 13.6.41. Consider the ellipsoid and the point P on the level curve. Compute the slope of the line tangent to the level curve at P and verify that the tangent line is orthogonal to the gradient at that point. Ouch, I could barely say that, let alone take it all in at once. Instead of taking it all in at once, let's just look at it piece by piece. First, let's look at the ellipsoid. To be exact, it's the top half of an ellipsoid. Second, they're wanting us to consider level curves. Here are quite a few of level curves. And they want us to look at a particular level curve. So they want to look at this function and a level curve of this function. So you can see what I'm going to do. I'm going to set these two things equal to each other. You can go ahead and stop the video and do it yourself. Set them equal to each other and see what happens. Well, when the dust settles, I get an ellipse with points on the x-axis plus and minus 1, points on the y-axis plus and minus 2. And here's the level curve. Here's the level curve again, along with the equation of the ellipse. All right, now we've considered the ellipsoid, we've considered the level curve. Now they want us to look at this particular point on the level curve. And there it is. There's our level curve and our point. Now we're ready for the first question. What is the slope of the tangent line to the level curve at the given point? After all this footwork that we've done, the problem has really just reduced down to a Calculus 1 question. I'm going to use implicit differentiation to find the derivative, to find dy dx, and then I'm going to evaluate it at the given point. So if you want to practice that skill, go ahead and do that now. And here it is. I use implicit differentiation, solve for dy dx, and then evaluate it at the point. And this is the slope of the line tangent to the level curve at the given point. Now this is a side note. This is a piece of information that I know we're going to need later. Let's talk about a vector parallel to this tangent line. There's a whole bunch of vectors parallel to the tangent line. All I need is one, and I'm going to use a vector v equals run comma rise. And if you think about the slope of this vector, it would be the y component over the x component, and so I'd get that rise over run. So I'm looking at -2 over radical 3, and I make a vector out of that, and that vector is parallel to the tangent line. So I'm going to call, from now on, I'm going to call v. V will refer to the vector which is parallel to the tangent line of the level curve at the given point. Okay, so we have gotten our slope correct, and the next thing that we need to do is we need to say how we know the gradient and the tangent line are orthogonal? Well, first of all, what is the gradient? We haven't done any gradient work in this problem so far. So we have our given function and we need to find the gradient, and then we need to evaluate it at the particular point. So again, this is something that you can practice on your own. Find f partial x, find f partial y, and then we'll go on and do the evaluation. But for right now, just find f partial x and f partial y. And this is what I get. We next need to evaluate both partials at the given point. I'm going to take this one piece at a time. And you can do the whole thing and then follow along, or you can just do it one piece at a time with me. So just take that one expression and evaluate it at the point. After I evaluate the expression at the point, I get 15 over 16. Now that expression has to be raised to the negative 1/2 power. And so I just flip it and then take the square root of the top and the bottom. All right, now go ahead and evaluate the partials at the given point. And this is what I get. Once I do that, then I can find the gradient. I have brought a rather ugly scalar value to the outside of the vector. That's perfectly legal. It's a little different than how MML does it, but I kind of like it better this way. To determine if the gradient is orthogonal to the tangent line, all we need to do is to check to see if the gradient is orthogonal to our vector v, which is parallel to the tangent line. So how do we know that two vectors are orthogonal? See if you can rack your brain on that one. If you came up with the idea of taking the dot product, you're exactly right. If two vectors are orthogonal, their dot product is equal to 0. So I take the dot product of the gradient and this vector v, and I find that they are orthogonal. And that tells me that my gradient is orthogonal to the tangent line, because v was created so that it's parallel to the tangent line. So if those two vectors are orthogonal, then the gradient is orthogonal to the tangent line. And so I would choose B, and I would put the gradient vector into these blanks that they give us. Just a couple of notes. You might notice looking at this question, it says that for their vector v, they choose 1, m. That's fine. I prefer rise, run, rise. But any scalar multiple will work. We just need to have that ratio of -2 over radical 3 for the slope. Also, I brought my scalar value out, which you can't do for my math lab, so I've put it back in so you can see what it would need to look like. All right, well, I think that just about does it. Let me know if you have any questions.